Welcome, housing market analysts, to an insightful journey in our machine learning series. I'm thrilled to be here with you, and today we're diving into a regression task using a well-known dataset and a powerful explainability tool. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we predict house prices in California. Let's get started by setting up our environment and gathering our tools for this real estate analysis. I begin by installing the interpret library in Colab with a simple pip command. This library will help us with explainable AI, giving us insights into our model's decisions. Next, I import the essentials: NumPy for numerical operations, pandas for data manipulation, and Sklern's fetch California housing function to access our dataset. From Sklern, I also bring in train test split to split our data, random forest regressor for our model, and our to-score and mean squared error to evaluate performance. From interpret, I import partial dependence from the black box module, our tool for global explanations, along with the show function to display results. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render directly in Colab. I also set a random seed with NumPy's random seed, set to 42 for reproducibility. With our toolkit ready, let's load the data. I load the California housing dataset using Sklern's fetch California housing function. I create a data frame with the feature names provided by the dataset: Medinc for median income, house age, AVA rooms for average rooms, AVA bedrooms, population, AVA cup for average occupancy, latitude and longitude, and add the target column, which is the median house value in hundreds of thousands of dollars. I print the first few rows to take a look. The first row shows Medinc 8.3252, house age 41.0, AVA rooms 6.984127, latitude 37.88, longitude minus 122.23, and target 4.526. That's $452,600. The next row has Medinc 8.3014, house age 21.0, and target 3.585, $358,500. This dataset contains 20,640 samples of California block groups from the 1990 census, with 8 features and a target ranging from 0.15 to 5.0, making it a great dataset for predicting house prices. Let's prepare the data for modeling. I split the dataset into features and target. X is all columns except the target, the 8 features, and Y is the target, house value in hundreds of thousands. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 16,512 training samples and 4,128 test samples. The features are all numeric, and there are no missing values, so we're ready to train our model. I initialize a random forest regressor from Sklern with 100 estimators and random state 42. Random forest regression is an ensemble method that builds multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It averages their predictions to reduce overfitting and improve accuracy, making it ideal for regression tasks like predicting house prices, where features like median income and location may have complex, nonlinear relationships with the target. I call fit on X-train and Y-train to train the model, letting it learn how features like Medinc and latitude influence prices. Once trained, I make predictions on X-test with predict, storing them in Y-pred, and evaluate with our to-score and mean squared error. The results are solid. Our to-score is 0.8051 to 80.51% of the variance explained in the test set, a good performance. Mean squared error 0.2554. Take the square root, about 0.505 or $50,500, which is reasonable for house values ranging from $15,000 to $500,000, though it indicates some error on high-value homes. I use partial dependence from Interpret's black box module to explain our model's behavior globally. Partial dependence is an explainability tool that shows the marginal effect of a feature on the predicted outcome, averaging out the effects of all other features. It helps us understand how a feature like Medinc impacts house price predictions across its range, revealing trends and nonlinear relationships. I initialize partial dependence with our model's predict function, xtrain as the background data, and the feature names from xcolumns. I generate a global explanation with explain global and visualize it with show. On screen, you're seeing the partial dependence plot from Medink, one of the 8 features analyzed. The title reads name, Medink type, continuous hashtag unique, 10932, indicating Medink has 10,932 unique values in the training set. The x-axis shows Medink values from 0.5 to 15, with specific points like 1.6, 1.821, 2.482, up to 13.7 and 15. The y-axis shows the average response, the predicted house value, from 0 to 4.5. The plot has a blue line with a shaded confidence interval, showing how the predicted price changes with Medink. At Medink 0.5, the average response is around 1.0, $100, 000. As Medink increases to 2.0, the response rises to about 1.5, $150, 000. There's a steep jump between Medink 2.0 and 4.0, where the response climbs to 2.5, $250, 000, showing a strong positive effect. From Medink 4.0 to 8.0, the response gradually increases to around 3.5, $350, 000, with a slight plateau. Beyond Medink 8.0, the response flattens, hovering around 4.0, $400, 000, up to Medink 15, indicating a ceiling effect where higher incomes don't increase prices much further. Below the plot, an orange histogram shows the distribution of Medink values, with most data concentrated between 1.0 and 5.0, fewer samples at higher values like 10.0 to 15.0, which explains the wider confidence intervals at those extremes. This plot reveals Medink as a key driver of house prices, with a nonlinear relationship, strong growth up to a point, then diminishing returns. Let's reflect on these outputs. They're a roadmap for California's housing market. The first row showed a house with Medink 8.3252, house age 41.0, latitude 37.88, and target 4.526, $452, 600, while the next had Medink 8.3014 and target 3.585, $358, 500, indicating high-income areas have higher prices. The R2 score of 0.8051 means our model explains 80.51% of the price variance, and the mean squared error of 0.2554 translates to an average error of $50,500. Decent, but with room for improvement on high-value homes. The partial dependence plot from Medink showed a steep rise in predicted price from $100,000 at Medink 0.5 to $250,000 at Medink 4.0, then a slower increase to $400,000 at Medink 15 with a plateau effect. The histogram confirmed most Medink values are between 1.0 and 5.0, aligning with the steeper part of the curve. Partial dependence's global view helps us understand how features like Medink incorporated drive predictions across the dataset, making our random forest behavior interpretable. To wrap up this housing market analysis, we've explored the California housing dataset, a 20,640 sample study of 1990s California block groups, and train a random forest regressor, achieving an R2 score of 0.8051 and mean squared error of 0.2554. The global explanation via partial dependence revealed Medink's strong, nonlinear impact on house prices, offering a clear view into our model's trends. Random forest regression's ensemble approach captured complex housing patterns, and partial dependence marginal effect analysis provided transparency for our black box model. Grab this code, explore other features like latitude, and dive deeper into housing predictions. I'm inspired by this real estate dive. Hope it's got you thinking about data's role in market analysis. See you next time for another data-driven exploration.